Are we alone in the universe? Is Earth, this extraordinary planet that hosts us, so unique? This question, as old as humanity itself, has taken on a new dimension with the birth of a revolutionary science, the hunt for exoplanets. Some could be similar to our Earth. Others, however, defy the imagination, even of the most visionary thinkers. Dear traveler, a friendly hello. Today we embark towards our cosmic neighbors. But before we set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a nice trip. What exactly is an exoplanet? The term, a contraction of external and planet, simply refers to a planetary body orbiting a star other than our sun. These extrasolar worlds, sometimes called new Earths or super-Earths, represent the ultimate frontier of modern space exploration. The idea that other worlds might exist beyond our solar system is not new. As early as antiquity, philosophers like Epicurus speculated on the existence of infinite worlds. In the 16th century, Giordano Bruno dared to assert that stars were distant suns, potentially surrounded by their own planets. But it was only at the dawn of the 21st century that science was able to confirm these millennia-old intuitions. The quest for exoplanets was long hindered by colossal technological obstacles. How do you spot a tiny rocky point, lost in the cosmic immensity, overshadowed by the dazzling light of its star? It's like trying to distinguish a firefly flying in front of a lighthouse, thousands of kilometers, thousands of miles away. The challenges seemed insurmountable, yet human ingenuity triumphed. Astronomers, by developing cutting-edge observation techniques, made the impossible possible. The radial velocity method, which measures the tiny wobble of a star caused by the gravity of its planets, paved the way. Then, the transit method was developed, scrutinizing the dimming of a star's brightness when a planet passes in front of it. These techniques, coupled with ever more sophisticated instruments, triggered a veritable avalanche of discoveries. The first exoplanet, orbiting a star similar to the Sun, was spotted in 1995. Since then, an astronomical revolution has been underway. Dedicated space missions like Kepler and TESS have detected thousands of new worlds. Each discovery brings its share of surprises and challenges our certainties about the formation and evolution of planetary systems. Today, we know that exoplanets are the norm, rather than the exception. More than 5,500 exoplanets have been confirmed and cataloged. From hot Jupiters to mysterious super-Earths to potentially habitable worlds, our galaxy is teeming with planets with fascinating characteristics. Some experience rains of liquefied iron, while others could harbor oceans of liquid water. The exploration of exoplanets doesn't just satisfy our cosmic curiosity. It allows us to better understand our own planet and our place in the universe. Each new finding brings us perhaps closer to the answer to this fundamental question: does life exist elsewhere? In 1992, the history of modern astronomy took a dramatic turn with the announcement of a major discovery, that of the first exoplanets. The identification of PSR B1257 plus 12b, C, and D not only marked a milestone in our quest to understand the universe, it also redefined the boundaries of what seemed possible. At that time, exoplanet research was a nascent field. Detection techniques were still limited, and astronomers faced substantial technological challenges. It was then that Alexander Wolszczan and Dale Frail, two visionary astrophysicists, scrutinized a pulsar named PSR B1257 plus and 12, located about 2,300 light-years from Earth in the constellation Virgo. To recall, a pulsar is the stellar remnant of a massive star that exploded as a supernova. with a mass greater than that of the Sun, although its average size is about that of the modest island of Rhe, approximating just 34 square kilometers or 13 square miles. It spins on its axis at a dizzying speed. This ultra-dense remnant, among the fastest objects in the universe, emits radio waves at regular intervals. It was precisely this rhythmic cadence that allowed Wolfschan and Frail to detect anomalies in the periodicity of the signal, suggesting the presence of objects orbiting the pulsar, and these objects turned out to be planets. PSR B1257 plus 12 as a pulsar is nothing like a classical star. It's a stellar corpse, a neutron ball spinning on its axis at an incredible speed, about 160 times per second. At first glance, it seemed implausible that planets could exist around such an object. And yet, analyses confirmed the presence of 3 rocky planets. PSR B1257-B, the most modest of the 3, would almost make Mercury look like a giant. Its mass is estimated at only 0.02 times that of Earth. It orbits at a distance of about 0.19 AU, approximately 18 million miles, just slightly closer to its pulsar than Mercury is to the Sun. On this planet, whose year lasts only 25 Earth days, an infernal environment reigns supreme. The light from the pulsar does not warm its soil as a classical star would, but bombards its surface with deadly radiation. Under these hostile conditions, the planet is very likely to appear as a barren desert, covered with rocks vitrified by millennia of exposure to these energetic rays. The gravitational forces of the pulsar maintain it on a stable orbit, but its desolate landscape, plunged into perpetual night by the absence of true light, evokes a world frozen in time. PSR B1257-12C is a moderate giant, with a mass about 4 times that of Earth. It is a significantly more imposing planet. It orbits farther, at 0.36 AU, approximately 33 million miles, completing a full revolution in 66 Earth days. This rocky planet might be a veritable labyrinth of canyons and craters, carved by the intense bombardment of particles from the pulsar. Its surface, covered with dark minerals, must faintly glisten under the effect of the radiation, a spectacle both fascinating and frightening. The powerful gravitational forces of the pulsar have likely crushed any atmosphere it might have had, leaving its surface exposed to devastating stellar winds. Despite its larger size, this planet is a perfect example of the harshness of an environment where life seems to have no chance of flourishing. The farthest of the 3, PSR B1257-12D, orbits at 0.46 AU, approximately 43 million miles, and completes its orbit in 98 Earth days. Its mass is similar to the previous one, but its more distant location gives it unique characteristics. This planet, likely an icy sphere locked in absolute cold, is far from any heat source. Yet, beneath its frozen appearance, it might harbor fascinating secrets. Gravitational forces and tides induced by the pulsar could generate internal geological activity. One can imagine geysers of material erupting on its surface, creating fleeting spectacles in the midst of this inhospitable universe. Its relative distance slightly protects it from the most intense radiation, but not enough to make it a viable refuge. These 3 worlds, though different, share a common origin: the chaotic debris of a destroyed star. Each planet tells a story of survival in a brutal universe where even stellar ruins can become places of infinite fascination. The existence of these planets has indeed greatly surprised the scientific community. because this revelation has challenged many hypotheses about planetary system formation and survival. Until then, most astronomers expected to find planets around so-called classical stars, like the Sun, but not alongside pulsars. The environment around a pulsar is so hostile that the formation, or even the persistence, of planets alongside it was deemed impossible. The existence of these planets raises questions about their formation. Did they survive the supernova explosion that created the pulsar, or did they form from the debris of the explosion? This second hypothesis seems to be the most likely for researchers. Ejected materials could have coalesced to form these planets, proving that worlds can emerge even after a stellar cataclysm. The discovery of these 3 planets marked a turning point in exoplanet research. It paved the way for a new era of cosmic exploration, prompting scientists to expand their field of investigation. No longer limited to sun-like stars, every corner of the universe could now be scrutinized in search of unknown worlds. It also allowed for the development of new technologies and methodologies. Pulsars, with their regular signals, have proven to be remarkably precise astronomical beacons for detecting small gravitational perturbations caused by planets. Finding an exoplanet is like searching for a needle in a haystack, furthermore, in total darkness. But human ingenuity has overcome this spatial obstacle. Since the first discoveries, astronomers have developed revolutionary methods to reveal these hidden worlds. Here is an overview of the most emblematic techniques, from the most classic to the most daring. Let's start with the radial velocity method. Imagine a solitary star, majestically reigning in the vastness of space. But here's the thing. If a planet orbits around it, this star is no longer as immobile as it seems. The planet's gravity exerts a slight pull on the star, causing it to wobble subtly. These tiny movements are the key to the radial velocity method. Astronomers observe the star's light, analyzing its spectrum to detect periodic shifts. If the star is moving away, the light shifts to the red. If it is approaching, it leans towards blue. This cosmic wobble betrays the presence of a planet, even if the planet itself remains invisible. It is thanks to this method that the first exoplanet around a classical star, 51 Pegasi b, was discovered in 1995. Modern instruments, like the HARPS spectrograph, can measure velocity variations on the order of a few centimeters per second or a few inches per second, allowing the detection of Earth-sized planets. Another method employed is that of transits. Have you ever seen an eclipse? When the moon passes in front of the sun, it blocks part of its light. The transit method relies on this same principle. If a planet passes in front of its star, even briefly, it causes a minute drop in brightness. Astronomers thus scrutinize the light from stars, looking for these tiny variations. When a transit is detected, it provides a wealth of information: the size of the planet, its orbit, and even the composition of its atmosphere if the latter filters the starlight. This method exploded with the Kepler mission, which discovered thousands of exoplanets by analyzing the light from more than 150,000 stars. Thanks to it, we have detected worlds as diverse as scorching hot Jupiters and potentially habitable super-Earths. Albert Einstein's general theory of relativity offered another ingenious method for tracking exoplanets: gravitational microlensing. When a massive star passes in front of a more distant star, its gravity acts like a magnifying glass, amplifying the background light. If a planet orbits the massive star, it can produce a slight perturbation in this light amplification. It's like a drop falling into a perfectly calm lake. One observes a tiny, yet revealing, wave. This technique is rare because it relies on an almost perfect alignment between the stars. However, it is incredibly powerful for detecting planets located thousands of light years away from us, including rogue planets, those solitary worlds wandering through space without orbiting a star. Finally, direct imaging allows us to photograph the invisible, or nearly so. The idea of capturing an image of an exoplanet seems almost too good to be true. How can we distinguish a tiny planet drowned in the blinding light of its star? Astronomers use advanced techniques to block this light, such as coronagraphs and interferometers. These tools allow the direct observation of giant planets located far from their star in the infrared. One of the first direct images of an exoplanet was obtained in 2004, a massive world orbiting the star 2M 107. Today, instruments like SPHERE, installed on the Very Large Telescope in Chile, further push the boundaries, offering us stunning images of distant planetary systems. However, each method has its strengths and weaknesses. Radial velocities and transits are ideal for studying planets close to their star, while microlensing and direct imaging explore the far reaches of the cosmos. Together, they map a universe where each star could well harbor astonishing worlds. Thanks to these techniques, what once seemed unreachable is now a tangible reality. And each new detection promises even more incredible discoveries to come. The Kepler mission, launched by NASA in 2009, decisively marked the hunt for exoplanets. This revolutionary space telescope tirelessly observed a small portion of the sky for nearly 4 years, simultaneously observing more than 150,000 stars. Its method? Detecting the minute drops in brightness caused by a planet passing in front of its star. This transit technique, applied on an unprecedented scale, enabled a spectacular harvest of discoveries. Kepler not only confirmed that exoplanets were ubiquitous in our galaxy, but also revealed a staggering diversity of these worlds. Indeed, it led researchers to rethink their understanding of planetary formation. Among Kepler's most fascinating discoveries is Kepler 16b, nicknamed the Tatooine planet, in reference to the fictional world from Star Wars. Detected in 2011, this gas giant the size of Saturn orbits not one, but 2 stars. This binary system, located about 200 light-years away from Earth, offers an extraordinary celestial spectacle, 2 suns rising and setting in a perpetual cosmic ballet. Kepler 16b completes a full revolution around its pair of stars in 229 Earth days, skillfully navigating a zone where its orbit remains stable despite the gravitational complexity of the system. This discovery proved that planetary formation was possible even in multiple stellar environments, significantly broadening our conception of potential solar systems. One of the most promising super-Earths identified to date is Kepler 442b, discovered in 2015. Orbiting around an orange star, cooler and less luminous than our Sun, this exoplanet is less than half the Earth-Sun distance from its star, or about 46 million miles. This distance from its star places it comfortably in the system's habitable zone. With a radius estimated to be nearly 1.34 times that of Earth and a mass probably 2.3 times greater than our planet, Kepler 442b presents characteristics that make it very interesting for the search for potentially habitable worlds. Its surface gravity, slightly higher than Earth's, could allow for the retention of a substantial atmosphere. One of the most fascinating aspects of Kepler 442b is its Earth Similarity Index, estimated at 0.84, on a scale from 0 to 1. This high value suggests potentially favorable conditions for the emergence and maintenance of life as we know it. The surface temperature, though estimated to be slightly colder than Earth's, could allow for the presence of liquid water, this precious and essential ingredient for life. Located about 1,200 light-years away, unfortunately, this exoplanet remains out of reach for direct exploration with our current technologies. Future generations of telescopes could allow us to learn more about its atmosphere and composition. And who knows? Maybe one day we will be able to answer this famous question: are we alone in the universe? Also, in 2015, another planet made headlines upon its discovery. Here is Kepler 452b, an exoplanet nicknamed Earth's cousin. Orbiting around a star very similar to our Sun, this super-Earth is also located in the habitable zone of its system, about 1,400 light-years away from us. With a radius 60% larger than that of Earth and a year of 385 Earth days, Kepler 452b presents fascinating specifics. Its mass, estimated at 5 times that of Earth, suggests a surface gravity about twice as high as ours. The venerable age of its star, around 6 billion years, suggests the possibility of prolonged evolution, potentially sufficient for the development of complex life forms. Although probably rocky, Kepler 452b could experience intense volcanic activity, significantly impacting its surface and atmosphere. Out. Discovered in 2017, here is Kepler 1652b, a super-Earth that stands out for its orbit around a red dwarf. Located more or less 822 light-years from Earth, this exoplanet has a radius about 1.6 times larger than that of our planet. It completes a full revolution around its star in 38.1 days, placing it in the potentially habitable zone of the system. The peculiarity of Kepler 1652b lies in the nature of its host star, an M2V-type red dwarf, whose stability and longevity could also offer favorable conditions for the development of life. With an estimated equilibrium temperature of around 34 Celsius or 93 degrees, Kepler 1652b should be able to support liquid water on its surface, although its size suggests it could be more like a mini Neptune rather than a rocky planet. Now, let's take a look at Kepler 1649c. Discovered in 2020, it's one of the most promising Earth-like analogs identified to date. Located just 300 light-years from Earth, this exoplanet orbits a red dwarf in the habitable zone of its system. With a radius only 1.06 times greater than that of Earth, and receiving 75% of the solar energy our planet receives, Kepler 1649c presents striking similarities to our world. Its year lasts only 19.5 Earth days, reflecting its proximity to its host star. Despite the challenges posed by the potentially intense activity of its red dwarf, such as frequent stellar flares, Kepler 1649c remains a serious candidate in the search for habitable worlds. Its late discovery, due to an initial classification error, highlights the importance of reanalyzing existing data. Finally, let's focus on K2 360b. Initially detected in 2016, it has recently been the subject of a more in-depth study revealing extraordinary characteristics. This super-Earth, located about 800 light-years from us, presents a record density, suggesting a unique internal composition. With an estimated radius 1.5 times that of Earth and a mass 7.7 times greater, K2 360b is one of the densest exoplanets known to date. Researchers believe it could harbor a global magma ocean beneath a thin crust, likely resulting from a gigantic impact or extreme proximity to its star during its formation. Orbiting very close to its host star with a period of only 21 hours, K2 360b undergoes intense radiation bombardment, which, as a result, renders its surface inhospitable. On the contrary, it proves to be a unique laboratory for studying the evolution of planets under extreme conditions. While the Kepler mission has offered us a fascinating glimpse of the diversity of extrasolar worlds, one discovery in particular captivated the world's attention. This discovery revolutionized our understanding of planetary systems and, consequently, our quest for extraterrestrial life. Welcome to the extraordinary universe of TRAPPIST-1. In 2017, a sweeping announcement shook the scientific community. The discovery of a miniature solar system containing not one, not two or three, but 7 Earth-sized planets. TRAPPIST-1, named after the telescope that allowed its initial detection, is an ultra-cool dwarf star located only 39 light-years from Earth. What makes this system fabulous is the configuration of its planetary objects. Indeed, the 7 detected planets orbit very close to their host, in a space more confined than Mercury's orbit around our Sun. Despite this proximity, the low luminosity of TRAPPIST-1 allows 3 of these worlds, TRAPPIST-1e, F, and G, to evolve in its habitable zone, where conditions might be conducive to the existence of liquid water on the surface. TRAPPIST-1e, in particular, has sparked intense interest. With a radius and mass very close to those of Earth, it receives a quantity of stellar energy similar to that perceived by our planet. Models suggest it could harbor oceans and an atmosphere, among other things. In short, favorable conditions for life. This discovery has major implications for the search for extraterrestrial life. The fact that 7 Earth-sized planets can coexist so close to their star reconfigures our previously established models. But above all, it considerably broadens the range of possibilities in terms of habitability. As the Kepler telescope bows out after a decade of groundbreaking discoveries, a new mission is taking over to continue the search for exoplanets. Launched in 2018 by NASA, the Transiting Exoplanet Survey Satellite, or TESS, was designed to scan almost the entire sky in search of exoplanets transiting around a certain category of stars. Unlike Kepler, which observed a restricted area, TESS adopts a broader approach, monitoring about 85% of the sky. To cover such a vast research area, the sky is divided into 26 sectors, which are observed one by one, each for 27 consecutive days. This strategy not only allows the detection of a large number of exoplanets, but also targets stars that are close and bright enough to allow detailed follow-up studies. With its increased sensitivity and extensive coverage, TESS is opening a new era in the exploration of interstellar worlds, promising even more puzzling discoveries. Let's begin the tour of these revelations by turning our gaze to TOI 700d. Discovered in January 2020, this planetary object represents a major advance in the search for Earth-like exoplanets. This planet, the first Earth-sized one discovered by this mission in the habitable zone, orbits around TOI 700, a red dwarf with a rather calm temperament. Located in the constellation Dorado, it is about 101.4 light-years or 607 trillion miles away from us. TOI 700d thus has a radius about 1.2 times that of Earth and completes a full orbit around its star in 37 days. Its position in a favorable zone is particularly interesting because it receives from its star about 86% of the energy the Earth receives from the Sun. This configuration should allow the presence of liquid water on its surface, an essential element for life. The host star, TOI 700, has a mass and size about 40% of those of our Sun, with an estimated surface temperature that's half as high. Its relative stability is a major asset for the potential habitability of TOI 700d, as many red dwarfs are known for their rather fiery nature, manifesting as intense stellar activity. Climate simulations carried out for TOI 700d have revealed a variety of possible scenarios. In some, the planet appears as an oceanic world, while in others, it could be bathed in an atmosphere dominated by carbon dioxide, similar to Mars in its distant past. These different possibilities make TOI 700d a prodigious subject for study for upcoming observation missions. Among the particularly intriguing discoveries of the TESS mission, we can also mention TOI 733b. Discovered in 2019, it represents a most unusual class of exoplanets, transitioning sub-Neptunes. Orbiting around a G-type star located about 245 light-years or 1,439 trillion miles from Earth, this planet is in a critical phase of its evolution, offering astronomers a unique opportunity to study atmospheric loss processes. TOI 733b has a radius about 2 times that of Earth and completes a full orbit around its star in just 4.9 days. This proximity to its host star exposes the planet to intense radiation, causing significant heating of its upper atmosphere. But TOI 733b is singularly fascinating for another reason. In reality, it is found in what scientists call the Neptune Desert. This region, where there is a rarity of intermediate-sized planets between super-Earths and Neptunes, is assumed to be the result of atmospheric erosion due to intense stellar radiation. Observations of TOI 733b suggest that it is actively losing its atmosphere. This atmospheric loss could, in the long term, transform this mini-Neptune into a rocky super-Earth, thus providing a real-time glimpse into planetary evolution. Therefore, the study of TOI 733b could help us understand why our solar system does not contain planets of this size. Thus, it would allow us to fill an important gap in our understanding of the formation and evolution of planetary systems. Moreover, it could provide clues about the processes that shape the long-term habitability of planets. Another fascinating object of study for astronomers is TOI 238b. Discovered in 2023, it is a hot super-Earth that orbits a K-dwarf, this type of star being slightly smaller and cooler than our Sun. Located about 235 light-years from Earth in the constellation of Eridanus, this exoplanet presents unique characteristics. Its radius, estimated to be about 1.5 times that of Earth, places it squarely in the super-Earth category. It completes a full orbit around its star in just 1.3 days, which means it is extremely close to its host star. This proximity implies that TOI 238b receives a deluge of radiation, making it a world probably very hot and inhospitable to life as we know it. In reality, the particular interest of TOI 238b lies in its host star. K-dwarfs are considered promising targets in the search for habitable exoplanets. They are more stable and have a longer lifespan than the smaller red dwarfs, while being numerous and bright enough to allow detailed observations. Although TOI 238b itself is too hot to be habitable, its study could provide valuable insights into the formation and evolution of planets around this type of star. The composition and structure of TOI 238b are subject to much speculation. Its density, once accurately determined, could indicate whether it is a primarily rocky planet or if it has a significant gaseous envelope. In any case, the intense radiation it receives from its star likely has a major impact on its atmosphere and surface geology. The study of TOI 238b is part of a broader effort aimed at understanding the diversity of planetary worlds in our galaxy. It helps us refine our models of planetary formation and evolution and better understand the conditions that could favor or hinder the development of life on other worlds. In June 2022, the discovery of the exoplanet TOI 1452b quickly captivated the attention of astronomers worldwide. Located about 100 light-years from Earth in the constellation of Draco, this super-Earth presents characteristics that make it a potential candidate for being an ocean world. TOI 1452b orbits a red dwarf star in a binary system, completing a revolution in just 11 days. Despite this proximity to its star, the low brightness of the latter places TOI 1452b in its habitable zone, where conditions could permit the existence of liquid water on its surface. More interesting still is its density. With a radius about 70% larger than that of Earth and an estimated mass nearly 5 times that of our planet, its density suggests a composition rich in water. Models indicate that up to 30% of its total mass could consist of water, a proportion far greater than that of Earth, which is only 0.02%. The idea of an ocean world like TOI 1452b enthralls scientists, as it offers an environment potentially conducive to the emergence and maintenance of life. Deep oceans could provide protection from cosmic radiation and offer a stable environment for the development of complex ecosystems. Furthermore, the discovery of TOI 1452b underscores the importance of international collaborations in the search for exoplanets. Initially detected by TESS, its nature was confirmed through follow-up analyses conducted by the Mont Mégantic Observatory in Quebec. demonstrating the crucial role of ground-based observatories in the characterization of exoplanets. In-depth study of TOI 1452b could teach us more about the formation and evolution of water-rich planets. Could this type of world, which does not exist in our solar system, be common in our galaxy? The question remains open and encourages us to broaden our criteria beyond simple Earth analogs. The prestigious discoveries of TESS have given us a glimpse into the diversity of worlds populating the Milky Way. Among these exoplanets, one category in particular is drawing increasing interest: super-Earths. These planets, more massive than Earth but less imposing than gas giants like Neptune, represent a missing link in our understanding of the formation and evolution of planets. With masses typically ranging from 1.5 to 10 times that of Earth, or from 3,300 to 22,000 pounds, super-Earths could be promising candidates for harboring life, while presenting characteristics radically different from our planet. If you are ready, let us explore these enticing worlds. In this multitude, could one of these super-Earths be revealed as our cosmic cousin? Let us start with Proxima Centauri b, our closest extrasolar neighbor, located only 4.2 light-years, or 25 trillion miles from Earth. Discovered in 2016, this super-Earth orbits Proxima Centauri, the smallest star in the Alpha Centauri triple system. With two suns setting on its horizon, its landscapes are bathed in hypnotic blood-red light. Its position in the habitable zone of its star, theoretically allowing it to harbor liquid water on its surface, makes it a remarkable subject of study. However, the proximity to its red dwarf presents specific challenges. Proxima b is likely in synchronous rotation, irreversibly exposing one face to its star. This creates a striking contrast between a hemisphere that is perpetually burning and another plunged into icy cosmic night. The frequent flares of Proxima Centauri bombard the planet with intense radiation, raising questions about the possibility of maintaining a stable atmosphere. Despite these significant challenges, Proxima b remains our best chance to study in the near future a potentially habitable exoplanet. There is no doubt that this super-Earth will be a priority target for future observation missions. At 97 light-years or 570 trillion miles from Earth, the GJ9827 system offers us a unique cosmic laboratory to study the formation and evolution of super-Earths. Discovered in 2017, this system harbors 3 planets with exceptional characteristics. All orbit a K-dwarf star in less than 6.2 days. GJ9827b, C, and D form a chain of planets whose sizes range from 1.6 to 2 times Earth's radius. This configuration is particularly intriguing because it integrates the Radius Valley, a mysterious scarcity of planets with sizes between 1.5 and 2 Earth radii, or between 6,334 to 8,300 miles. Studying these 3 worlds could help us understand the processes that determine whether a planet retains its primordial atmosphere or becomes a barren rocky body. Observations suggest that GJ 9827b could be a hot, rocky super-Earth, while D, and potentially C, could have retained part of their primordial gaseous envelope. This system offers a rare opportunity to study planets at different stages of evolution orbiting the same star. Over time, it will undoubtedly allow a better understanding of the factors that influence the destiny of super-Earths. In the cosmic dance of exoplanets, HD 40307G stands out as a particularly graceful dancer. Located 42 light-years, or 247 trillion miles away in the Painter constellation, this super-Earth orbits an orange dwarf star, smaller and cooler than our Sun. What makes HD 40307G so intriguing is its ideal position in the Goldilocks zone of its system. Neither too close nor too far from its star to allow for the potential existence of liquid water on its surface, we may have discovered a temperate super-Earth. With an estimated mass of at least 7 times that of Earth, or at least 15,000 pounds, it is at the upper limit of the super-Earth category. Its orbit, lasting 197.8 days, places it in a region where it could potentially maintain a non-synchronous rotation, thus avoiding the trap of always showing the same face to its star. This feature could favor a more uniform distribution of heat on its surface, increasing its chances of habitability. Although we do not yet know its exact composition, models suggest that HD 40307G could be a rocky world with a substantial atmosphere, or even an ocean world covered with a thick layer of water. Its discovery highlights the diversity of potentially habitable planetary environments beyond our solar system. In the bestiary of exoplanets, one stands out as a prodigious anomaly. Discovered in 2021, GJ 367b is a sub-Earth that challenges our planetary formation models with its extraordinary density. Orbiting a red dwarf just 31 light-years from Earth, GJ 367b completes a revolution in just 7.7 hours. It is one of the exoplanets with the shortest known orbital period. This peculiarity places it in the category of so-called ultra-short period planets. But what makes GJ 367b a truly unusual planetary object is its composition. With a radius of about 72%, or 45 miles, that of Earth, and a mass equivalent to 55% of our planet, its density is comparable to that of pure iron. This characteristic suggests that GJ 367b could be the stripped core of a once larger planet, whose atmosphere and mantle were torn away by the intense radiation of its star. The study of GJ 367b offers us a glimpse of the extreme processes that can significantly impact planetary evolution. Its proximity to Earth makes it a prime target for future observations, which could help us unravel the mysteries of its formation and internal composition. On the contrary, a super-Earth caused a sensation in the scientific community in 2019 for its enigmatic atmosphere in which traces of water vapor were detected. This is K2-18b, an exoplanet discovered a little earlier in 2015. It orbits in the habitable zone of a cool red dwarf located in the constellation Leo, 124 light-years away. With a radius about 2.6 times that of Earth, or 10,388 miles, and an estimated mass of 8.6 Earth masses, K2-18b lies at the boundary between super-Earths and mini-Neptunes. Its density suggests an intriguing composition, probably a rocky core surrounded by a vast liquid ocean, all enveloped in a thick atmosphere of hydrogen and helium. The detection of water vapor in its atmosphere, a first for a potentially habitable planet, has opened new perspectives in our quest for hospitable worlds. However, the conditions on its surface remain a mystery. The intense atmospheric pressure could create a hostile environment with extreme temperatures and oceans in an exotic state called supercritical fluid. K2-18b illuminates the fact that habitability can take forms we have not yet imagined. This distant world thus pushes us to broaden our conception of what constitutes a life-friendly environment. Another planetary object pushes the boundaries of what we thought we knew about the composition of super-Earths. Our exploration of super-Earths has revealed a troubling diversity of potentially habitable worlds. Nevertheless, the universe teems with exoplanets with even more extreme and unimaginable characteristics. Welcome to WASP 121b, a hot Jupiter discovered in 2015, which pushes the limits of what we thought possible for a planet. Orbiting its star in just 30 hours, WASP 121b is so close to its sun that its surface temperature exceeds 2,500 degrees or 4,532 degrees. In essence, it is hot enough to melt most metals. But if this planet is truly unique, it is due to the shape of its atmosphere. Observations from the Hubble Space Telescope revealed that the intense heat and gravitational force of the host star deform its atmosphere, giving it the appearance of a rugby ball. This distortion is so extreme that the planet's atmosphere is escaping into space, leaving behind a trail of hot gases. Even more fascinating, WASP 121b is the first exoplanet where heavy metals, such as iron and magnesium, have been detected escaping from the atmosphere. This phenomenon offers scientists a unique opportunity to study atmospheric evaporation processes and the evolution of planets in such environments. If this planet seems extreme to you, another one pushes the concept of an infernal planet even further. Here is WASP 76b, an ultra-hot gas giant discovered in 2013. With an orbit completed in just 1.8 days, it is so close to its star that its daytime temperature reaches 2,400 degrees Celsius or 4,352 degrees Fahrenheit. But even more extraordinary is its unprecedented meteorological cycle. On this planet, it literally rains liquid iron. How is this possible? The answer lies in the massive temperature difference between the day side and the night side of the planet. WASP 76b is in synchronous rotation with its star, always presenting the same face to it. On the day side, the intense heat vaporizes all metals, including iron. These metal vapors are then carried by violent winds to the cooler night side. There, they condense into droplets of liquid iron that fall in an infernal rain before evaporating again when they reach warmer regions. This extreme meteorological cycle creates a sharp boundary between the day side and the night side, where scientists have detected a strong asymmetry in the presence of iron vapor. This discovery unveils a stunning sample of atmospheric processes at work on ultra-hot planets. Let's leave this burning hell now to visit a world of another nature. Before you is GJ 1214b. This super-Earth, discovered in 2009, might well be entirely covered by a vast ocean. Located only 40 light-years from Earth, this planet orbits a red dwarf in the constellation of Ophiuchus. With a radius 2.7 times that of Earth and a mass 6.5 times greater, GJ 1214b falls into an intermediate category between rocky super-Earths and gaseous mini-Neptunes. But it's its low density, suggesting a water-rich composition that makes it truly unusual. Models indicate that GJ 1214b could be composed of up to 75% water, far more than Earth's 0.02%. However, do not expect to find familiar oceans on this world. Due to its proximity to its star, the surface temperature of GJ 12114b is estimated to be around 200 degrees or 392 degrees. Under these extreme conditions, water probably exists in an exotic state called supercritical fluid, where the distinctions between liquid and gas blur. The planet's dense and opaque atmosphere could be composed of water vapor and clouds of liquid water in suspension. GJ1214b alone proves that the idea of planets offering environments conducive to life, particularly those rich in water, is not a fantasy. While most of the exoplanets we have explored are mature worlds, one of them offers us a rare opportunity to observe a planet in full formation. Discovered in 2018, Ci Tau b is a gas giant orbiting a young star barely 2 million years old in the constellation of Taurus. Ci Tau b is what is known as a hot Jupiter, a giant gas planet orbiting very close to its star. But, unlike its older counterparts, Ci Tau b is still in its formation phase, capturing gas and dust from the protoplanetary disk surrounding its star. The mass of Ci Tau b is most intriguing. At about 11.6 times the mass of Jupiter, it sits on the boundary between a planet and a brown dwarf. This discovery challenges our understanding, as it was considered unlikely that such a massive planet could form so close to its star. The study of Ci Tau b could help us understand how hot Jupiters form and migrate inward in their systems. It also raises fascinating questions about the early evolution of planetary systems and the mechanisms that determine the final mass of a planet. Among the most extreme worlds in our galaxy, 55 Cancri E holds a special place. Discovered in 2004 and confirmed in 2011, this super-Earth defies our imagination with its hellish conditions. Orbiting its star in just 18 hours, 55 Cancri E is so close to its sun that its surface temperature reaches 2,400 degrees or 4,352 degrees Celsius. At this temperature, the rock itself melts, creating an ocean of lava that likely covers the entire surface of the planet. The potential composition of this planetary object is even more unbelievable. Some models suggest that a significant part of this planet could be composed of diamond. In the extreme pressure and temperature conditions of 55 Cancri E, carbon could crystallize into diamond, creating a literally precious world. Recent observations have revealed intriguing variations in brightness, suggesting that 55 Cancri E could have a thin and dynamic atmosphere despite the intense heat. This atmosphere could be composed of vapors of rocks and metals, constantly renewed by the evaporation of the molten surface. Who would have dared to imagine one day that such a world could exist? In this extreme environment, such geological and atmospheric processes can only lead us to push the limits of our speculations further and further. Among these extreme worlds, not all resemble deserts of flames, where the slightest breath of air turns into a burning wind, capable of consuming everything in its path. The arrival of the James Webb Space Telescope marks a new era in the study of exoplanets, opening up unprecedented perspectives on these distant worlds. Launched in December 2021, this successor to the Hubble telescope pushes the boundaries of astronomical observation thanks to its unique capabilities. It is distinguished notably by its primary mirror, which is 6.5 meters or 21 feet in diameter, composed of 18 hexagonal segments made of beryllium and coated with gold. This collecting surface, nearly 7 times larger than Hubble's, gives it exceptional sensitivity. Moreover, its instruments are optimized for observing in the infrared, a crucial range of wavelengths for the study of exoplanets. This sensitivity allows it to penetrate cosmic dust veils and observe colder and older objects than ever before. For exoplanets, this means it can detect and analyze their atmospheres with unprecedented precision. One of its first significant discoveries in the field of exoplanets concerns WASP-39b, a hot Jupiter located 700 light-years away from Earth. In August 2022, the telescope made the first unequivocal detection of carbon dioxide in the atmosphere of this exoplanet. This discovery demonstrates the James Webb Telescope's ability to identify specific molecules in exoplanetary atmospheres. Thus, it paves the way for the search for biosignatures on potentially habitable worlds. This engineering tool has also brought fascinating revelations regarding K2-18b, a super-Earth located in the habitable zone. The telescope's observations allowed the identification of methane and carbon dioxide in its atmosphere, reinforcing the hypothesis that K2-18b might be an oceanic world. These results highlight the potential of this telescope to study exoplanets that could harbor life. In the realm of direct imaging, James Webb achieved a feat by observing AF Leporis b, the lowest mass exoplanet ever directly imaged by this telescope. This ability to directly see increasingly smaller planets opens new perspectives for detailed study of planetary systems. The James Webb Telescope has also offered us incredible discoveries, such as the identification of GJ 9827d as a steam world, a type of exoplanet never observed before. This planet, whose atmosphere is primarily composed of water vapor, represents a missing link in our understanding of planetary evolution. Another remarkable first is the observation of the thermal emission of TRAPPIST-1b, this Earth-sized planet, as cold as the rocky planets in our own system. This ability to detect thermal radiation from relatively cold, small planets is crucial in our quest for potentially habitable worlds. Among the most recent discoveries, James Webb has provided compelling evidence of the existence of a global ocean on LHS 1140b, a super-Earth located 49 light-years away from us. The observations revealed spectral signatures consistent with the presence of a water vapor-rich atmosphere above a vast ocean. This discovery is particularly exciting, as LHS 1140 Cas-b orbits in the promising zone of its star, making it an attractive candidate for habitability. This cosmic eye has also taken a new look at 55 Cancri e, this infernal super-Earth we previously explored. The new observations of its atmosphere revealed unexpected temperature variations between the day side and the night side, suggesting the possible presence of a thin atmosphere capable of redistributing heat. These results challenge our understanding of ultra-hot planets and their ability to retain an atmosphere in extreme conditions. The prospects for studying exoplanetary atmospheres with this space observatory are dizzying. The sensitivity and spectral resolution of the telescope will not only allow for the detection of atmospheres on increasingly smaller and more distant planets, but also for the detailed analysis of their chemical composition. This capability is crucial in the search for biosignatures, those chemical markers that could indicate the presence of life. In the future, this telescope could allow us to study the atmospheres of rocky planets in the habitable zone of nearby stars, like those of the TRAPPIST-1 system. Detection of molecules like oxygen, methane, or ozone in these atmospheres could provide the first tangible evidence of the presence of life beyond our solar system. As the James Webb Telescope continues to push the boundaries of our understanding of exoplanets, ground observatories and space missions are not to be outdone. In recent years, there has been an explosion of fascinating discoveries, each adding a piece to the complex puzzle of the diversity of worlds that populate our galaxy. Let's dive into the latest revelations that shed light on our understanding of the exoplanet universe. In May 2022, the HD 260655 system made a splash in the astronomical community with the discovery of two fascinating exoplanets. Located just 33 light-years from Earth, HD 260655b and HD 260655c are among the closest and easiest to study rocky exoplanets ever discovered. HD 260655b, the inner planet, has a radius about 1.2 times that of Earth and orbits its star in just 2.8 days. Its surface temperature is estimated at 435 degrees Celsius, or 815 degrees Celsius, making it a scorching world, probably inhospitable to life as we know it. Its sister, HD 260655c, is slightly larger with a radius 1.5 times that of Earth and an orbital period of 5.7 days. Although less exposed than its inner neighbor, with a temperature estimated at 284 degrees or 543 degrees Celsius, it remains too hot to be considered potentially habitable. Despite their extreme temperatures, these planets are of paramount importance to the science of exoplanets. Their proximity and the brightness of their host star make them ideal targets for detailed studies of rocky exoplanet atmospheres. Future observations could help us understand how planets evolve and lose their atmospheres in extreme environments. In September 2022, an exciting discovery captured the scientific community's attention. Let me introduce you to LP890-9c, also known as Speculoos 2c. This super-Earth, located just 100 light-years from us, orbits in the habitable zone of its ultra-cool dwarf star. What makes LP890-9c particularly enticing is its size, about 40% larger than Earth, and its optimal position in the habitable zone of its system. Models suggest it could maintain surface temperatures conducive to the existence of liquid water, this essential ingredient for all forms of life. The host star of LP890-9c, a red dwarf, is remarkably calm for its type, reducing the risks of devastating stellar flares. This stability increases the chances that the planet could have retained an atmosphere over the long term, an essential factor for habitability. The relative proximity of LP890-9c makes it an ideal target for future atmospheric studies with the James Webb Telescope. These observations could offer us the first clues about the composition of the atmosphere of a potentially habitable super-Earth. Might we one day detect some encouraging biosignatures? In February 2023, the discovery of Wolf 1069b rekindled the hope of finding life near our solar system. This super-Earth, located just 31 light-years from us, orbits in the habitable zone of its red dwarf star. Wolf 1069b stands out for its resemblance to our Earth. With an estimated mass of 1.26 times that of our planet, it could have a comparable composition and surface gravity. Its year of 15.6 Earth days places it comfortably in the zone where liquid water could exist on the surface. The host star of Wolf 1069b, although cooler and less massive than our Sun, exhibits relatively low activity for a red dwarf. This feature increases the chances that the planet could have retained a stable atmosphere over the long term, a crucial factor to make it habitable. The proximity of Wolf 1069b is a considerable advantage. New generation telescopes could be capable of detecting the presence of an atmosphere and analyzing its composition. Will the first clues of the presence of life on this exoplanet reveal themselves one day? Discovered in 2023, LP791-18d represents an impressive category of exoplanets, volcanically active worlds. Located about 86 light-years from us, this super-Earth orbits around a cold red dwarf in just 2.9 days. LP791-18d stands out for its presumed intense volcanic activity. Researchers estimate that this planet could be subject to tidal forces so powerful that they would cause a constant deformation of its internal structure, generating considerable heat. This phenomenon, similar to what we observe on Io, Jupiter's moon, could fuel spectacular volcanic activity on the surface of LP791-18d. This explosive activity could then have prodigious implications for habitability. On one hand, it could create a constantly regenerating atmosphere, potentially rich in compounds necessary for life. On the other, the intense activity could make the surface inhospitable, relegating any potential form of life to underground or underwater niches. The study of LP 791-18d offers a unique opportunity to observe the geological evolution of a planet in real time, helping us better understand the processes that shape rocky worlds, including in our own solar system. The year 2024 began in January with the announcement of a discovery by NASA that immediately captivated the attention of exoplanet hunters, TOI 715b. This super-Earth, located about 137 light-years from us, orbits in the habitable zone of a red dwarf. TOI 715b stands out for its size, about 1.5 times larger than Earth, placing it in the super-Earth category. It completes a full orbit around its star in just 19 Earth days, receiving an amount of energy comparable to what our planet receives from the Sun. TOI 715b is particularly interesting because of its optimal position in the habitable zone. Models suggest that it could maintain surface temperatures conducive to the existence of liquid water, this vital ingredient. The host star of TOI 715b, although smaller and cooler than our Sun, presents relatively stable activity for a red dwarf. This characteristic increases the chances that the planet could have retained an atmosphere over the long term. The James Webb Telescope might tell us a little more about its atmosphere in the near future. A few months later, two extraordinary new super-Earths were announced by NASA, TOI 6002b and TOI 5713b. These discoveries, made thanks to the TESS Space Telescope, illustrate the growing diversity of worlds we are discovering in our galactic neighborhood. TOI 6002b, located about 172 light-years away, has a radius about 1.65 times that of Earth and a mass nearly 4 times greater. It orbits around an M dwarf in 10.9 days, with an estimated equilibrium temperature of 48 degrees Celsius or 118 degrees Celsius. This relatively moderate temperature makes it an interesting candidate for the study of temperate super-Earths. Its cousin, TOI 5713b, is slightly smaller but just as intriguing. With a radius about 77% larger than that of Earth and a mass estimated at 4.3 Earth masses, it completes an orbit in 10.44 days. Its equilibrium temperature, calculated at 74.1 centigrades or 165 degrees, places it in a category of hot planets, but still potentially suitable for detailed atmospheric studies. These two planets offer a unique opportunity to study the evolution of super-Earths under different conditions. Their discovery highlights the increasing efficiency of our detection methods and promises new revelations on the formation and diversity of planetary systems. The future of exoplanet research looks exciting, with many technological and scientific advancements on the horizon. As we continue to push the boundaries of our knowledge, new space missions and improved detection techniques are emerging. By focusing more on the characterization of exoplanetary atmospheres, these advances promise to revolutionize our understanding of worlds beyond our solar system. Among the most anticipated space missions is the European Space Agency's planetary transits and oscillations of stars. The launch of Plato, scheduled for 2026, promises to discover and characterize Earth-sized planets and super-Earths orbiting in the habitable zone of Sun-like stars. This mission could offer us the first true Earth 2.0, worlds sufficiently similar to ours to potentially harbor life. The Aerial Space Telescope, for atmospheric remote sensing infrared exoplanet large survey, which is set to launch in 2029, will focus on studying exoplanetary atmospheres. By observing a large number of exoplanets simultaneously, Ariel will allow us to understand how planetary systems form and evolve, and how atmospheric conditions vary from one planet to another. On Earth, the next generation of giant telescopes, such as the European Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope, promise to revolutionize our ability to study exoplanets from the ground. With primary mirrors ranging from 30 meters or 98 feet to 40 meters or 131 feet in diameter, these telescopes will have the power needed to directly image exoplanets and study their atmospheres in detail. Detection and analysis techniques continue to improve at a rapid pace. Artificial intelligence and machine learning play an increasingly significant role in the analysis of exoplanetary data, allowing the detection of fainter signals and the characterization of smaller and more distant planets. Methods like very long baseline interferometry could soon allow us to map the surfaces of nearby exoplanets, revealing the presence of continents, oceans, or even, dare we imagine, artificial structures. The characterization of exoplanetary atmospheres is becoming increasingly central to our quest to understand these distant worlds and search for signs of life. Future missions and observation techniques will focus on detecting biosignatures, these chemical markers that could indicate the presence of living organisms. The simultaneous detection of gases like oxygen, methane, and carbon dioxide in the atmosphere of a rocky planet in the habitable zone would be a strong indication of biological processes. Just 3 decades ago, we knew of no planets beyond our solar system. Today, we have confirmed the existence of over 5,500 exoplanets, with thousands more candidates awaiting confirmation. This explosion of discoveries has completely transformed our understanding of the formation and evolution of planetary systems. We have learned that planets are common in our galaxy. The diversity of worlds we've discovered far exceeds what we could have envisaged based solely on our solar system. From hot Jupiters to super-Earths to potentially habitable worlds like Proxima b or TRAPPIST-1e, each revelation broadens our conception of what is possible in the universe. This exoplanetary revolution also has profound philosophical implications. The discovery of many potentially habitable worlds renews with particular urgency the question of our place in the universe. Are we truly alone? If life existed elsewhere, what form could it take? These questions, once in the realm of pure speculation, are becoming progressively accessible to scientific investigation. From a scientific standpoint, the study of exoplanets has led to a more nuanced understanding of habitability. We realize that the traditional habitable zone is just a starting point. Factors such as geological activity, atmospheric composition, or even the presence of moons could play an essential role in a planet's potential to host life. The search for extraterrestrial life, long confined to science fiction, is now a legitimate and expanding scientific field. Future space missions and new generation terrestrial observatories bring us closer to the day when we might detect the first signs of existence beyond our solar system. Even in the absence of the discovery of extraterrestrial life, the study of exoplanets will continue to enrich our understanding of the universe and our own world. Every planet we study is a cosmic laboratory, offering us insights into the physical, chemical, and potentially biological processes that shape worlds. The future of exoplanetary research promises not only groundbreaking scientific discoveries, but also a profound transformation of our vision of the universe and ourselves.